It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we introduced the star player of computer vision, the Convolutional Neural Network, or CNN. We established what it is, a specialized neural network architecture inspired by the human visual cortex, designed specifically to process grid-like data, such as images. We discussed its key insight, this idea of a spatial hierarchy. The network learns simple features like edges first, then combines them into more complex features like shapes and textures, and finally combines those into full object parts. We named the unique building blocks that make this possible, the convolutional layer and the pooling layer, but we left them as conceptual black boxes. We said, these layers do the work, but we didn't peek inside. Today, we open the engine compartment. The what is complete. Now we begin the how. Think about the last time you saw a self-driving car navigate a busy street. In a fraction of a second, it identifies a pedestrian waiting to cross, registers the traffic light turning from green to yellow, and tracks the car ahead of it, all while staying perfectly in its lane. Or consider a simpler, everyday miracle. You upload a photo from a crowded concert to your social media, and before you can even type a caption, the platform has correctly identified and tagged half of your friends. This isn't magic. It's a beautiful intersection of mathematics, computer science, and biology. These marvels are powered by a field called computer vision, and at the very heart of this revolution is the CNN. This brings us to the core question. How do you take a machine, an entity that understands the world only as a series of numbers, and give it the gift of sight? How do we translate the fluid, intuitive, and incredibly complex act of human vision into the rigid logic of algorithms? The answer lies not in one single breakthrough, but in a series of elegant, powerful building blocks. Our learning objective for today is to deconstruct, piece by piece, the two primary mechanisms that power a CNN. First, we will understand, pixel by pixel, how the convolutional layer acts as a set of feature detectors. Second, we will discover why its essential partner, the pooling layer, is so critical for making those detections efficient, manageable, and robust to real-world messiness. By the end of this episode, you will have the core intuition for how an AI system truly begins to see. Let's start with the absolute foundation. We have an input image. To a computer, this isn't a cat or a tree. As we've discussed, it's just a grid of numbers. If it's a grayscale image, it's a single two-dimensional grid, where each number represents a pixel's brightness, maybe 0 for pure black and 255 for pure white. If it's a color image, it's 3 of these grids stacked on top of each other, like 3 pancakes. One grid represents all the red values, one for all the green, and one for all the blue. This stack of grids, this three-dimensional volume of numbers, is our input. Now, enter the star of today's show, the filter, which is also called the kernel. To understand the convolutional layer, I want you to imagine a detective arriving at a crime scene, and this crime scene is our image. The detective knows that to solve the case, they can't just glance at the entire room at once. The truth is in the details, the clues. So, they pull out a set of specialized magnifying glasses. Each magnifying glass is designed to spot a very specific type of clue. One is etched to highlight vertical lines. Another is built to find horizontal edges. A third is designed to spot gentle curves. These magnifying glasses are the kernels or filters of a convolutional layer. In practice, this filter, this kernel, is just another grid of numbers, but a small one. Typically, it might be 3 pixels by 3 pixels, or maybe 5 by 5. These numbers in the filter are the weights. Now here's the magic of deep learning, the revolution that separates this from old-school computer vision. When a network is first created, the weights in these kernels are completely random. They are useless magnifying glasses. But during the training process, using an algorithm called backpropagation, which we explored back in episode 13, the network learns. It adjusts the values in these kernels over and over until they become highly specialized feature detectors. The network discovers on its own that detecting vertical lines or 45-degree lines or little curves is a useful intermediate step for its final goal of classifying the image. The filters are learned parameters. So, how does this filter, this little 3x3 grid of weights, actually work with the image? This is the convolution operation. Let's stay with our 3x3 filter. We take this filter and we place it over a 3x3 patch of the input image. We'll start at the very top left corner. This 3x3 patch of the image that the filter is currently looking at is called the receptive field. Now we perform a simple, two-step mathematical operation. Step 1. We do an element-wise multiplication. This sounds fancy, but it just means we multiply the numbers that are in the same position. The top left pixel value of the image patch is multiplied by the top left weight of the filter. The top middle pixel is multiplied by the top middle filter weight. The top right pixel by the top right weight, and so on for all 9 pairs. We now have 9 new numbers, the products of those multiplications. Step 2, we sum them all up. We add all 9 of those products together to get one single number. That single number is the result of the operation for that one position. It represents the score of how much that image patch matched the filter's pattern. A high value means a strong match. A low value or negative value means no match. This single number, this one summary score, becomes the first pixel in our new output grid. This new grid is called the feature map, or sometimes the activation map. We've only calculated the top left pixel of our new feature map. What's next? We slide the filter. We move our 3x3 filter 1 pixel to the right, so it's now covering the next 3x3 patch, and we repeat the entire process. Element-wise multiplication, sum them all up. That result becomes the second pixel in our feature map, right next to the first one. We slide, calculate, all the way across the first row. When we hit the right-hand edge, we move the filter down 1 pixel all the way back to the left-hand edge, and we begin scanning the second row. We repeat this process like a typewriter or mowing a lawn, until we have scanned the entire input image. The result is a brand new grid of numbers, the feature map. What does this map represent? If the filter we used was one that had learned to detect vertical edges, this new feature map will be a grid that is bright, has high values wherever a vertical line was present in the original image, and dark, has low or 0 values everywhere else. We have created a map of that feature's locations. Now I have a little secret to share, a detail that often gets glossed over but reveals something fundamental about the philosophy of deep learning. The operation I just described, the one used in virtually every major deep learning library like TensorFlow and PyTorch, isn't technically a convolution. It's an operation called cross-correlation. What's the difference? It's subtle but mathematically precise. A true pure convolution requires you to take the kernel matrix and flip it, both horizontally and vertically, before you start the sliding and multiplying process. Cross-correlation skips this flipping step entirely. In traditional signal processing, that flip is critical. It gives the convolution operation certain mathematical properties that are very important. So why do deep learning frameworks skip it? The answer lies in the learnable nature of the network. The weights in the kernel aren't fixed, they are learned during training. If the ideal filter for detecting a feature is a specific matrix, a network trained with cross-correlation will simply learn that exact matrix. If it were trained with true convolution, it would just learn the flipped version of that same matrix to achieve the identical result. The network's ability to detect the feature remains the same. By skipping the flip, the operation becomes computationally simpler and faster to implement. This is a perfect example of a pragmatic engineering decision, trumping pure mathematical formalism. The field of deep learning often prioritizes what works efficiently at a massive scale. So, while we call them convolutional neural networks, out of historical convention, it's more accurate to think of them as cross-correlation neural networks. This is a reminder that the goal here isn't just mathematical purity, it's building systems that learn effectively. The true power of a CNN layer doesn't come from just one filter. A single convolutional layer is composed of many filters, all working in parallel. We might decide, as the architects of the network, that our first layer will have, say, 32 filters. This means we take our input image and we perform that entire sliding window operation 32 separate times. Each of the 32 filters has its own set of learned weights. Each one learns to look for a different feature. So, filter number 1 might learn to detect vertical edges. Filter number 2 learns horizontal edges. Filter number 3 learns a 45-degree edge. Filter number 4 learns a small, tight curve. Filter number 5 learns a patch of green. Filter number 6 learns a transition from blue to red, and so on. The output of this single convolutional layer, therefore, isn't a single feature map. If we had 32 filters, the output is a stack of 32 feature maps. It's a new 3D volume of numbers. Each slice in this volume is a map showing where one specific, simple feature was located in the input. There's one more small, but crucial step in the convolutional layer. After we perform the operation, the multiply and sum, to get a single number, we pass that number through an activation function. We covered these back in episode 14, the spark of nonlinearity. In traditional neural networks, we often used functions like sigmoid or tanh. In modern CNNs, the undisputed champion is the ReLU, which stands for rectified linear unit. It's an incredibly simple function. It just says, if the number you're given is positive, keep it exactly as it is. If the number is negative or 0, change it to 0. Why do this? First, it introduces the same critical nonlinearity that all neural networks need to learn complex patterns. But more intuitively, for a feature map, it makes perfect sense. It means we only want to record the presence of a feature. A negative score, meaning this is the opposite of the feature, is just treated as the feature is not present. The resulting feature map becomes sparse, meaning it's mostly zeros, with positive spikes of high value only in the places where the feature was strongly detected. This makes the network's computations much more efficient. So the full process for one filter is convolve, or rather cross-correlate, and then activate ReLU. The output is a clean map of where that feature was positively found. Now, as an AI architect, you have a few dials you can turn to control how this operation behaves. These are the hyperparameters of the layer. Two of the most important are stride and padding. Let's start with stride. Think of stride as the detective's step size. A stride of 1 means the detective slides their magnifying glass over by just 1 pixel at a time, ensuring they meticulously examine every single spot on the image. This is the most detailed approach. But we could choose a stride of 2. In this case, after we calculate the first pixel of our feature map, we would slide the filter 2 pixels to the right, skipping the position in between. Then we'd slide another 2 pixels. We'd do the same when moving down the image. What's the effect? Our resulting feature map will be roughly half the width and half the height of the input. This is a powerful way to make the network smaller and faster. We're essentially saying, I don't need to check for this feature at every single pixel location. Checking every other pixel is good enough. It's a classic balance between thoroughness and efficiency, but it also means you might miss some fine-grained details. The second hyperparameter is padding. Now, imagine the detective trying to center their magnifying glass on a pixel at the very edge of the photo. Part of the glass would hang off the edge. This is a problem. Without a solution, the pixels on the border of the image are seen far fewer times than the pixels in the center. Furthermore, every time we perform this operation, the output feature map is slightly smaller than the input image. If we have a very deep network with many layers, our image could shrink until it disappears entirely. The solution is padding. It's like taking our crime scene photo and taping a blank border around it. The most common technique is zero padding, where we add a border of pixels with a value of 0 all around the image. This ensures that the kernel can be centered on every single pixel of the original image, from the corners to the center. It also gives us control over the output size. By choosing the right amount of padding, we can ensure the output feature map has the exact same height and width as the input image, a technique called same padding. This is crucial for building the very deep networks that power modern AI. If we use no padding, it's called valid padding, which just means the output will be smaller. So, our detective, the convolutional layer, has done its job. It has scanned the image with dozens of different magnifying glasses and produced a thick stack of feature maps, each one highlighting the location of a specific clue. This is a lot of information, potentially millions of data points. The network can easily get overwhelmed by this level of detail. This brings us to the second key component, the pooling layer. After our convolutional layer, we have this big stack of feature maps. For example, if our input was 100 by 100 by 3, and we used 32 filters with same padding and a stride of 1, our output is now 100 by 100 by 32. We've actually expanded the data in the depth dimension. This stack is detailed, but it has two problems. Problem 1. It's computationally expensive. The next convolutional layer will have to process this big 100 by 100 by 32 volume. Problem 2. It's too sensitive. The feature maps record the exact location of the features. If the original image of a cat shifts 1 pixel to the right, the vertical line feature from its ear will also shift 1 pixel to the right on the feature map. We want our network to be robust. We want it to recognize a cat regardless of whether it's perfectly centered or slightly off to the side. The pooling layer is the brilliant, simple solution to both problems. It is a downsampling or subsampling layer. It acts like the next step in the detective's process, creating a summary report. Instead of listing every single piece of evidence in excruciating detail, the detective divides the crime scene map into a grid of quadrants. Then, for each quadrant, they write down only the single most important finding. This act of summarizing and downsampling is the essence of pooling. The most common type of pooling by far is max pooling. Here's how it works. We take one feature map from our stack. We then define a pooling window, typically a 2x2 square. We lay this 2x2 window over the top left corner of the feature map. It covers 4 pixels. The pooling layer then asks a very simple question. Of these 4 numbers, what is the maximum value? Let's say the 4 numbers in the 2x2 patch are 0, 1, 15, and 3. The maximum value is 15. The max pooling layer discards the 0, 1, and 3, and it keeps only the 15. this single number, 15, becomes the top left pixel of its new, much smaller output map. Then, just like the convolutional filter, it slides. But a pooling layer's window typically has a stride equal to its size. So, a 2x2 pooling window will use a stride of 2. It jumps 2 pixels to the right, so it's looking at the next, non-overlapping 2x2 patch. It finds the max value of those 4 pixels, and that becomes the second pixel in its output. It tiles the entire feature map this way. The result is a new feature map that is half the width and half the height of the one it was given. We've just compressed the spatial information by 75%. We repeat this for all 32 feature maps in our stack. So our 100 by 100 by 32 volume becomes a 50 by 50 by 32 volume. It's much smaller and more computationally efficient for the next layer. But efficiency isn't even the most important reason we do this. The real magic is in what it does for robustness. This is how we get local translation invariance. This is a fancy term for a very simple and intuitive idea. An object is still the same object, regardless of where it appears in an image. Think about it. If you're trying to build a network to recognize cats, you don't care if the cat is in the top left corner of the photo or the bottom right. It's still a cat. Let's think about that 2x2 patch again. In the first case, the values were 0, 1, 15, and 3. The max value was 15. The output was 15. Now imagine the cat in the original image shifted 1 pixel. The feature map also shifts. That 15 moves. Our 2x2 patch might now look like this: 1, 15, 3, and 0. What's the max value? It's still 15. The output of the pooling layer has not changed. This is an incredibly powerful idea. The max pooling layer is essentially asking, was the feature I'm looking for present in this 2x2 neighborhood? Yes or no? Just give me the strongest signal of its presence. It's intentionally throwing away information about the exact pixel-perfect location in exchange for a more robust, general summary that says the feature was somewhere in this general area. By preserving only the strongest activation, it ensures that the most prominent, sharpest features are carried forward. Now, there is another type of pooling, called average pooling. As the name suggests, instead of taking the max value from the 2x2 patch, it takes the average of all 4 numbers. This gives a blurrier, smoother, more generalized summary. It was used in some early networks, but max pooling is generally preferred today because it tends to preserve more informative signals. This brings us to a crucial nuance and a common misconception. It's often said that because a CNN has pooling layers, it is automatically and perfectly translation invariant. The reality is more subtle. Pooling doesn't grant invariance, it encourages it. The operation is a somewhat crude form of downsampling. By taking a 2x2 region and collapsing it to a single pixel, the network literally throws away the information about where that maximum value was located within that 2x2 window. This forces the network to learn that the important thing is simply that the feature was present somewhere in that general vicinity. This loss of information is both a feature and a bug. For a task like image classification, is there a cat in this image? Losing the precise location of the cat's ear is not only acceptable but beneficial for generalization. But imagine a different task like medical image segmentation, where the goal is to outline the exact pixels that belong to the tumor. In this case, the loss of precise spatial information caused by pooling is a major drawback. This reveals a fundamental trade-off in network design: the balance between creating abstract, invariant representations for recognition and preserving the fine-grained spatial detail needed for localization. Pooling is a powerful architectural nudge in the right direction, but it's not a silver bullet. True invariance is an emergent behavior that the network must still learn from a diverse dataset. Another common misconception, especially when first learning this, is that alarm bell that goes off, "Wait a minute, you're telling me we just threw away 75% of our data, we had 4 numbers, and we just kept 1. That seems incredibly wasteful. How can discarding information possibly help?" This is a failure to distinguish data from information. We are discarding data points, but we are doing so to distill the information we actually care about. We are purposefully and strategically trading spatial precision for semantic robustness. We are telling the network, "I do not want you to memorize that a cat's ear is at pixel coordinate 5020. I want you to learn that a cat has a pointy triangle shape somewhere in the upper left quadrant." By forcing the network to be less precise with a pooling layer, we are forcing it to generalize. This makes it dramatically less likely to overfit the training data. The information we lost was actually just noise, pixel-perfect precision that would have hurt, not helped, the network's ability to generalize. To truly appreciate the elegance of these layers, we need to understand where they came from. This isn't an idea that sprang fully formed from a computer scientist's mind. It's a story that begins with biology. In the 1950s and 60s, 2 neuroscientists, David Hubel and Torsten Wiesel, conducted a series of Nobel Prize-winning experiments. They studied the brains of cats, specifically the visual cortex. What they found was revolutionary. They discovered that individual neurons in the visual cortex didn't respond to the entire visual scene. Instead, each neuron was responsible for a tiny, specific region of the visual field, which they called its receptive field. Furthermore, they found that these neurons were highly specialized. Some would fire only in response to a vertical line, others to a horizontal line. They also discovered a hierarchy. Simple cells responded to these basic lines, and complex cells responded to more abstract patterns over a larger receptive field. They were less picky about the exact location of the line. This biological architecture, a hierarchy of neurons that look at local regions and detect increasingly complex features, is the direct inspiration for the modern CNN. The first person to translate this biological blueprint into a computational model was a Japanese computer scientist named Kunihiko Fukushima. In 1980, he introduced a model he called the neocognitron. It was the true ancestor of today's CNNs. The neocognitron was the first model to explicitly use a deep hierarchical structure of 2 alternating types of layers. He called them slayers for simple cells, which performed feature extraction much like our convolutional layers, and clayers for complex cells, which performed downsampling to provide tolerance to shifts, just like our pooling layers. Architecturally, it was decades ahead of its time. However, it had one critical limitation. It lacked an efficient way to be trained. The powerful backpropagation algorithm had not yet been effectively applied to this kind of network. That brings us to the 1990s and to one of the godfathers of deep learning, Yann LeCun, working at the legendary Bell Labs. LeCun and his colleagues took the architectural ideas of the neocognitron and combined them with the backpropagation algorithm we discussed in episode 13. This was the crucial innovation. For the first time, they could train the weights of the convolutional kernels directly from data, allowing the network to learn for itself which features were important. This work culminated in 1998 with a landmark architecture called LeNet-5. Its mission was deceptively simple: to read handwritten zip codes on checks for the banking industry. It was one of the very first real-world, commercially successful applications of deep learning. Let's quickly walk through the structure of LeNet 5, because it perfectly illustrates how the layers we've discussed work together in a sequence. It starts with a 32 by 32 pixel grayscale image of a handwritten digit. The first layer, C1, is a convolutional layer with 6 5x5 kernels. It learns to detect basic features like edges and curves, producing 6 28 by 28 feature maps. The second layer, S2, is an average pooling layer with a 2x2 window and a stride of 2. This reduces the size of each feature map by half, resulting in 6 14 by 14 maps. This step provides some translation invariance. The third layer, C3, is a second convolutional layer, this time with 16 5x5 kernels. It processes the feature maps from the previous layer, learning to combine the simple features into more complex ones, like corners or loops. This produces 16 10-byte feature maps. The fourth layer, S4, is another 2x2 average pooling layer, shrinking the maps again, down to 16 5x5 feature maps. The final layers, C5, F6, and the output layer, are actually standard fully connected layers, like we learned about in episode 12. The 5x5x16 volume is flattened into a long vector and fed into these layers, which act as a classifier, taking the high-level features and making the final decision. Which digit from 0 to 9 is this? This history lesson reveals a profound truth about technological progress. The ideas behind CNNs, local receptive fields, feature hierarchies, downsampling existed for decades. The neocognitron was built in 1980, so why did deep learning only explode in the 2010s? The answer is computational power. LeCun's first network in 1989 took 3 full days to train. The real catalyst was the Graphics Processing Unit, or GPU-GPS, originally designed to render the complex 3D graphics in video games, happened to be extraordinarily good at the kind of parallel matrix multiplications that lie at the heart of deep learning. Around 2007, researchers began harnessing GPS for scientific computing, and suddenly training times plummeted. This created a powerful, self-reinforcing feedback loop. The availability of powerful hardware, GPS, made it feasible to train much deeper and more complex networks, algorithms. These deeper networks achieved breakthrough results, like the AlexNet model in 2012, which shattered records in image recognition. These stunning successes then drove massive investment back into creating even more specialized AI hardware. The story of CNNs is therefore inseparable from the story of computing hardware. So now, let's put it all together. We can finally see the full architecture of a CNN. It's not just one convolutional layer and one pooling layer. It's a stack of them, repeated over and over. A typical CNN block looks like this: convolution greater than ReLU greater than convolution greater than ReLU greater than max pooling. Let's trace the data through a couple of these blocks. We start with our input image. Let's say it's 224 by 224 by 3. Block 1, convolutional layer. We hit it with 64 filters, each 3 by 3. The output is a stack of 64 feature maps. Because we use same padding, the size is still 224 by 224. So our data is now 224 by 224 by 64. We also apply the ReLU activation at this step. 2. Max pooling layer. We apply a 2x2 max pooling operation. This halves the width and height. Our 224 by 224 by 64 volume becomes a 112 by 112 by 64 volume. This 112 by 112 by 64 volume is the input to the next block. What's in this volume? It's 64 maps, each showing the location of a simple, low-level feature: edges, curves, colors. Block 2, convolutional layer. We now hit this stack with a new set of filters, say 128 of them. These filters are also small. maybe 3 by 3. But think about what they are looking at. They are not looking at the raw pixels of the image. They are looking at the feature maps from block 1. 2. What does a filter learn to detect in a map of edges? It learns to detect combinations of edges. A filter in block 2 might learn to fire when it sees a horizontal edge feature directly on top of a vertical edge feature. In other words, it has learned to be a corner detector. Another filter might learn a series of small curves, becoming a texture detector. 3. The output of this layer, after its ReLU, might be 112 by 112 by 128. 4. Max pooling layer. We apply another 2 by 2 max pool. This halves the dimensions again. Our 112 by 112 by 128 volume becomes a 56 by 56 by 128 volume. This is the hierarchical feature extraction we've been talking about. Layer 1 filters look at pixels and find edges. Layer 2 filters look at maps of edges and find corners and textures. Layer 3 filters will look at maps of corners and textures and learn to find parts of objects. A filter might learn a circular feature next to a shiny texture feature, and in doing so, become an eye detector. With each block, the spatial dimensions, width and height of our feature maps get smaller and smaller, but the depth, the number of feature maps, gets larger and larger. We are squeezing the where information out and expanding the what information. We're trading spatial resolution for semantic abstract feature complexity. After several of these blocks, we might be left with a volume that is very small, say 7b7, but very, very deep, maybe 512. This 7b7 by 512 volume is an incredibly rich, dense, abstract summary of the original image. This final volume is then flattened, unrolled into one single long vector of numbers, and fed into a standard multi-layer perceptron, which makes the final classification. Now that we have deconstructed the mechanics, let's look at the payoff. How have these two simple layers, convolution and pooling, fundamentally changed our world? Perhaps the most profound impact of CNNs is in medicine, where they are acting as a powerful diagnostic aid for doctors. By training on vast libraries of medical scans, CNNs are learning to spot signs of disease with incredible accuracy, sometimes even exceeding that of human experts. They are being used to analyze mammograms, brain MRIs, and lung CT scans to identify tumors. They can analyze images of the retina to spot the subtle early warning signs of diabetic retinopathy, a leading cause of blindness. In autonomous systems, the primary vision system of a self-driving car is powered by CNNs. The core task here is object detection, not just classifying an image, but identifying multiple objects within it and drawing a bounding box around each one. All in real time, the car's cameras feed a continuous stream of data into highly optimized CNN-based models, which output classifications and coordinates for everything they see: other cars, pedestrians, cyclists, and traffic signs. This perception is the critical first step in the car's decision-making process. And of course, CNNs are invisibly woven into our daily digital lives. The automatic photo tagging on social media is facial recognition, where a CNN learns to extract the unique combination of features from a person's face. Visual search engines on platforms like Pinterest and Amazon use CNNs to analyze a photo of a chair you like and find visually similar items for you to buy. Looking at these examples reveals a deeper pattern. The true power of CNNs isn't just their ability to label an image, "This is a car" or "This is a tumor." Their transformative impact comes when this act of perception becomes the input for a larger decision-making system. This creates what we can call a perception-to-action pipeline. In medicine, a CNN detects a suspicious lesion. That's the perception. This perception informs a radiologist's diagnosis, the decision, which in turn leads to a specific treatment plan, the action. The CNN doesn't replace the doctor, it augments their ability. In a self-driving car, a CNN detects a pedestrian stepping into the road, perception. The car's control system then calculates the necessary speed and trajectory to avoid a collision, decision, and sends a signal to apply the brakes, action. The perception is useless without the ability to act on it. This shows us that convolutional and pooling layers are not an end in themselves. They form the foundational perception engine for a vast and growing range of intelligent systems. Before we wrap up, let's address a couple more common misconceptions. Myth 1. CNNs are only for images. This is perhaps the biggest one. While they were born from image processing, CNNs are incredibly effective at processing any data that has a grid-like structure. This includes unidimensional grids, like audio signals or financial time series data, and three-dimensional grids, like medical CT scans or video data, where time is the third dimension. Myth 2. Deeper is always better. It might seem intuitive that just stacking more and more layers will always lead to a better model. But in practice, very deep networks can become incredibly difficult to train effectively. Performance can actually get worse as you add more layers, unless you use clever architectural innovations, which we'll see in future episodes. So today, we have truly gone under the hood. We've deconstructed the two core components of machine vision. We've seen how the convolutional layer acts as a meticulous, learnable feature extractor, and we've seen how the pooling layer acts as its efficient partner, summarizing information, reducing complexity, and providing the crucial property of translation invariance. I want to leave you with one final metaphor to tie all of this together. The best way to think of a convolutional neural network is as an abstraction ladder. The network starts on the very bottom rung, with the raw, concrete, and meaningless pixel values of an image. The first convolutional layer climbs one rung up the ladder. It finds the first level of abstraction, simple patterns like edges, lines, and color gradients. The next layer takes those edges and lines and combines them, climbing another rung to find slightly more abstract concepts, corners, curves, and textures. Higher up the ladder, the layers combine those corners and textures to find recognizable parts of objects: an eye, a nose, a car's wheel, a building's window. Finally, at the very top of the ladder, the fully connected layers take these high-level abstract features and make a final semantic judgment. The collection of features I am seeing corresponds to the concept we call cat. This journey, from concrete pixels to abstract concepts, is the very essence of how machines learn to see. So far on our journey, from the first perceptron to the multi-layer perceptron to this complex CNN, we have been dealing almost exclusively with static data. A single row of numbers in a spreadsheet, a single static image, but the world we live in isn't static, it's a sequence. Language is not a single word, it's a sequence of words where order matters. Music is a sequence of notes. Our current architectures have no memory. A CNN processes every image from scratch. It has no concept of before or after. How do we build a network that can understand a sequence? How do we build a network that can remember what it saw 1 second ago, to inform what it understands now? That is the next great leap in our curriculum. We must move from the spatial to the temporal. We must build a network with a memory. We must build the recurrent neural network.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.